A buffer is a fascinating substance that has both a weak acid and its conjugate base, or a weak base and its conjugate acid. Now, strong acids and strong bases don't exist with each other at all, all right? They'll fight each other like constantly, and they'll destroy each other if they're ever around. But a weak acid and a weak base, they're like more mellow, and they will hang out with their conjugates in the same solution in general, which is pretty crazy. And when you create one of these buffers with a weak acid and its conjugate base, or weak base conjugate acid, these buffers will coexist and they resist changes to the pH of the solution. So if you add a strong acid, the weak base steps in to kick it out. And if you add a strong base, the weak acid steps in to kick it out. And they're amazing and they're super helpful. Our bodies are full of buffers. They keep our bodies safe and healthy and stuff like that, which is totally crazy. So up there in the picture, we have a 100 milliliter sample of dilute HCl, and we adjusted it to a pH of 5. So pH of 5 isn't super acidic, but it's hardly basic too. And so what we did there on the right there is you added a milliliter of either strong acid or strong base. And look what happens, man. The pH just went crazy. All right, you add a milliliter of the strong acid, the pH went down to 2. You add a milliliter of the strong base, and the pH went up to 12.0. So this is an example of a non-buffered solution, and just a milliliter will make the pH changes go crazy. Now here's an example, same kind of problem. We have 100 milliliters, so same volume, but this is an acetate buffer. This means that we have acetic acid and acetate, and it's been adjusted to a pH of 5. Now on the right, we have the same kind of conditions. We're adding a milliliter of strong acid or strong base to the same stuff, but look what happens. What made the pH go from 5 to 2 above went from 5 to 4.98 when we added the strong acid to the buffer. And what made the solution in the top go from a pH of 5 to pH of 12 upon adding sodium hydroxide? The pH of the buffered solution, 5.00 to 5.02. So buffers are really good about buffering your system. They're really good about resisting changes to pH. And if you have a living system, that can be super important. You don't want huge changes to your blood and your kidneys, stuff like that. So buffers are pretty important for our living bodies. Sodium acetate is added to an acetic acid solution. And the question is, what will be the pH of the solution? Will it go up? Will it go down? Will it stay the same, equal to 7, or do you need more information? Now, this is the kind of question that's going to be important to us. If you think about this, you are adding sodium acetate to something. We don't care about the acetic acid solution. We don't care what it's being added to. We want to know what we're adding. And we're adding sodium acetate. Now, if acetic acid is an acid, that means that sodium acetate is going to be a base. It's the conjugate base. We are adding a base, and bases will make your pH increase, all right? So think about how the pH is affected by what you're adding. You're adding a base, pH is going to go up. Adding an acid, pH is going to go down. If you look at the pictures in the upper right-hand corner, we added an acid, pH went down, 2.0. We added the base on the right, pH went up, 12.00. And even to the buffer solution, the pH changed a little bit too. Bases made it go up, acids made it go down. And it might be 0.000001 pH units, but it will go up or down because acids make pH goes down, bases make pH go up. Let's consider a buffer with some kind of random acid HA and the conjugate base A-. And let's say we're going to think about what happens if you have a strong base that's being attacked here. Now, strong bases are going to go after the weak acids, HA. So hydroxide will react with HA to make A- and water. And why this is important is that as you're adding a base to a weak acid, the weak acid steps up and neutralizes the hydroxide, but in the process, you're making conjugate base. Remember, if HA is the acid, then A- is the base. So adding hydroxide makes more of the weak base. And we'll come back to this here in a little bit. Now, if you add a strong acid, which is a source of H3O plus to your buffer, the weak base, A minus, steps up and it neutralizes it. However, in the process, you end up making more weak acid. So notice here that the strong base ended up making more weak base, and the strong acid ended up making more weak acid. So there is an effect on pH, although it's not quite what the strong acid and the strong base probably intended. So this is just kind of showing graphically here what's happening. In the upper part here, we're adding hydronium, a strong acid, and notice how the strong acid went up and the weak base went down. So bases and acids react, but in the process, more weak acid was made. And on the right-hand side, we've got the strong base hydroxide. The bases lowered the amount of acid, but they raised the amount of the conjugate base. And this is what happens with a buffer. You will see a pH change, but it's much more modulated thanks to the effect that these are weak acids and weak bases. So it's a fascinating process how this works, and it's incredible. And again, buffers are really important for life and a whole bunch of different things, which is really cool. If you're making a buffer, you must have a weak acid and its conjugate base, or a weak base and its conjugate acid. No strong acids and strong bases, they're not happy with their conjugates, but the weak acids and weak bases certainly are. Now, HOAC is going to be an abbreviation for acetic acid we'll use. Just kind of realize that's something we'll start talking about. OAC minus then would be the acetate ion. So you could have acetic acid and acetate, you could have dihydrogen phosphate and hydrogen phosphate, but you could also have a weak base and its conjugate acid, so ammonia and ammonium, and nitrite, NO2 minus, with nitrous acid, HNO2. All of these are examples. Now, we're going to mostly look at weak acids with conjugate base, but everything we talked about, you can also apply weak base and conjugate acid theory to it, but we'll focus mostly on a weak acid with a conjugate base. I do recommend that you check out this handout. It's called the Buffers and Henderson-Hasselbalch Guide. We're going to see how Henderson-Hasselbalch really helps with buffer calculations, and this handout also talks about what a buffer is, stuff like that. So which of these would be an ideal buffer solution? And again, a buffer needs to have a weak acid in its conjugate base, or a weak base in its conjugate acid, and certainly no strong acids and strong bases. And I'm hoping that you're seeing that there's lots of strong acids and strong bases in there. For example, HNO3. So that's not going to work. HNO3 is a hunter killer. It won't hang out with its conjugate. Nitrate is a conjugate, but it's not going to work. No strong acids, no strong bases. HCl and KOH are strong, so they're both out. That's not going to work. Let's skip to D real fast. D has ammonia, which is a weak base. And this crazy thing right here is what's called protonated methylamine. You don't need to worry about that. That is actually a weak acid. But the punchline here, NH3 has to be related by plus or minus an H plus to have a conjugate. And that thing is certainly not the conjugate. The conjugate of NH3 would be NH4 plus, the ammonium ion, all right? And the conjugate of this crazy thing, which you don't need to worry about, would be CH3NH2. Either way, these are not conjugates of each other. That's not going to happen. However, this last one on C, that's acetic acid. And if you take the Na plus off, CH3CO2 minus, that's acetate. Acetate and acetic acid are certainly conjugates. That's going to be a great combination. So again, weak acids with conjugate bases, or weak bases conjugate acids, and no strong acids, no strong bases. Must be conjugates. So let's say you want to find the pH of a buffer that has an acetic acid concentration 0.700 moles per liter and an acetate concentration 0.600 moles per liter. All right, no problem. What we would do is set up a Ka expression. The acid plus water makes the conjugate base plus hydronium. And the Ka for this value, 1.8 times 10 to the minus 5, which again you can look up in a table. So what you would do is set up an ice table. Initially, you have 0.700 moles per liter acetic acid, which we've done. But this reaction, we're also going to have 0.600 molar acetate. So they can coexist. As long as they're conjugates of each other and they're weak, they can get along. But we don't have any hydronium, and hydronium must be greater than 0 at equilibrium. So that's going to go up, and that's going to make the base go up to plus X, and the acetic acid here will go down by minus X. So here are the equilibrium concentrations. We can let all of those equal Ka. Ka would be 1.8 times 10 to the minus 5. That's going to equal hydronium, and what initially is 0.6 plus X, and on the bottom you'd have 0.7 minus X. However, X is going to be really small. If you have just almost equal amounts of acetate and acetic acid, then the X value here is going to be pretty small. So instead of dealing with 0.6 plus X and 0.7 minus X, you are justified in pulling both of those. So you end up with just Ka equals hydronium times the base, 0.6, divided by the acid, 0.7. So if you solve for hydronium, then hydronium equals Ka times the concentration of the acid divided by the concentration of the base, hydronium 2.1 times 10 to the minus 5, pH minus log of that number, 4.68. So the pH of this buffer system, 4.68. Cool. If you look at that expression carefully, the hydronium, H3O plus, equals the concentration of the acid divided by the concentration of the base times Ka. Remember, hydronium is the key to pH, and pH is really important. So if you can solve for an expression for hydronium, it's easier to find pH, which makes the chemist happy. Well, what scientists did is they rewrote this a little bit, and they let hydronium equals the acid over the conjugate base times Ka. And that's kind of interesting. Now, in terms of Kb, you can do it too. You'd have hydroxide equals base over conjugate acid times Kb, and that's fine. We're not going to talk about that version a lot, but it does work really well. But what I do want you to see is that the things that affect hydronium, say, is going to be twofold. It's going to be the ratio of the acid to the base and Ka. Now for hydroxide, it would be the ratio of the base to the acid times Kb. So you can affect the amount of hydronium, say, by changing the acid-base ratio, and you can also affect the amount of hydronium by changing the acid itself and its Ka value. But it's this ratio of two parts which is going to be really interesting, and the ratio of acid to base is going to lead to some really cool realizations for how buffers can be handled. So let's go back to the acid version. We're mostly going to focus on that. And hydronium equals the acid over the base times Ka. Well, one thing you can do is take the negative log of both sides of this reaction. Now, negative log hydronium is pH, and that's not a big deal. Minus log of the right-hand side, in the logarithm world, you can break that up. You can break that up into minus log Ka plus minus log acid over base. Now, minus log Ka is pKa. That's something we've seen a little bit or talked about. And minus log acid over base is the other part that's listed. So what happens a lot of times, people will flip the acid and base, and in the logarithm world, that turns the negative into a positive. You change the sign. So you end up with what's called the Henderson-Hasselbalch equation, pH equals pKa plus log base over acid. And this is one of my favorite equations, believe it or not, of the whole Chem 221 through Chem 223 series. It's for buffers. It can be used for other things too, but buffers is the primary thing. And it shows how the pH of a buffer depends on the pKa, the strength of the acid you put in, as well as the ratio of the base to the acid. And we'll talk about this here coming up. Henderson-Hasselbalch, the HH equation, is pretty cool because it really shows that the pH of a buffer depends on the ratio of the acid to base as well as the strength of the acid, the pKa. And they're kind of independent things. And we'll talk about how to make use of that here in just a second. But wow, the HH equation is the bomb when it comes to dealing with buffers. I'm letting you know that right now. Because it's a ratio, we usually use moles per liter over moles per liter. That's the standard ICE table kind of thing. But you don't really have to have concentrations of acid over base or base over acid. It really could be the ratio of moles. So you could have just the moles of base over moles of acid. So this gives you a lot of flexibility. You can use log concentration over concentration, but you can also use log of moles over moles. You can use the one which is easier. And because volume doesn't play a factor, you can take a buffer and just add a bunch of water to it, dilute the heck out of it. Doesn't change its pH, which isn't crazy. Now, if you made it like, the volume of, I don't know, Lake Erie or something like that, maybe there'd be some changes. But in a normal chemistry lab, you can just add tons of water, same pH, which is pretty crazy. Henderson-Hasselbalch is cool because, first of all, there's no effect on volume. You can add as much as you want, doesn't affect the pH. But also what's really important, you can use moles or molarity for acids and bases, whatever is easier for you. And that can have some serious implications, as we'll see in a little bit. Here's an example. We have acetic acid with a Ka value. Now, pKa equals minus log of Ka. So minus log 1.8 times 10 to the minus 5, 4.74. So that's where the pK value comes from. So we're going to prepare a buffer. It's got acetic acid and sodium acetate. Again, acetic acid is the acid, sodium acetate is the base. It's going to have a pH of 5. So what ratio of base to acid do we want? All right. So this question at first looks a little strange until you figure out how the Henderson-Hasselbalch works. We want a pH of 5. And that's going to equal pKa 4.74 plus log. And the ratio, I'm just going to call x, that's going to be the ratio of the base to the acid. So you want to solve for x. So 5 minus 4.74 will give you some number. You then get rid of the logarithm number by going 10 to the x. That's the anti-base 10 log. If you do all of that, you're going to get a ratio then of 1.8. So you can see once again what happened there. We wanted a pH of 5. pKa 4.74. 5 minus 4.74 is 0.26. And then to get rid of this base 10 log, you go 10 to the power of. So 10 to the power of log just cancels out. 10 to the 0.26, 1.8. So 1.8 is the ratio. And what that tells you is you want 1.8 times more base than acid. So if you put 1 mole of acid in, you want 1.8 moles of base in, stuff like that. It's pretty handy. It's a great way to figure out how much base and acid you can use, stuff like that. So here's a question. We want to figure out the pH when we add a milliliter of 1 molar HCl to a liter of pure water. And before it was HCl, we'll assume it was perfect at 7.00. But we also want to want the same 1 milliliter of 1 molar HCl to a liter of buffer that has acetic acid and acetate at those concentrations we used earlier. And we saw that they were pH of 4.68. All right, no problem. So to solve for the first one, pH to pure water, it's going to be minus log of hydroxide. So you need the moles of HCl, and you want to divide by the total volume. So if you do that then, first we're going to have to use M1V1 equals M2V2 to solve for the new concentration of the HCl. So 1 milliliter of 1 mole per liter HCl would be the M1 and V1. We're going to solve for M2 and the total volume, 1,000 plus 1, 1,001 milliliters. So the concentration comes out to be 9.99 times 10 to the minus 4 moles per liter, minus log of that number, pH of 7. So our 1 milliliter made the pH 7 drop to pH 3. Pretty heavy drop of pH. But again, this is the effect of strong acids. And again, non-buffered things will drop pretty fast if you have an acid added to them, or rise pretty fast if you add a base. But now let's do the same problem with our buffer. If you're going to do it this way, and I'll tell you a better way here in a little bit, first what you have to do is figure out the effect of the strong acid or strong base. So in this kind of problem, if you use moles per liter, the acetate, the base, is going to go down upon adding the hydronium. And it's going to use up all the hydronium because it's a hunter killer from HCl. So at the end, you're left with 0.599 moles per liter acetate. But as much as the base goes down, the weak acid is going to go up, because this is how buffers work. The strong acids wipe out some of the base, but in the process, the conjugate acid comes up. So you can see there what's happening. The acetic acid is going to jump then to 0.701. So these are our new concentrations after the HCl has been neutralized, and from this point now, we have to figure out what the new pH is. So at this point, we're going to go back to that acetic acid and water, making hydronium and acetate. We'll use the same things, but with our new values. So we're going to end up with 0.701 minus x, 0.599 plus x, and x. We can ignore that little x relative to 0.701 and 0.599 like we did in the last one, and we'll basically just solve for x, the hydronium. So if you do that, hydronium equals acid over base times Ka, 0.701 divided by 0.59 times the Ka. Hydronium comes out to be 2.1 times 10 to the minus 5, minus log of that number, and lo and behold, 4.68. And that was the pH before the HCl was added. So the buffer absolutely resisted the change of pH from the HCl. It dropped the water from pH 7 down to pH 3, but that same amount of acid didn't affect the buffer at all, and this just shows how powerful the buffers can be. Now the HCl did affect the buffer, all right? That's why the acetate went from 0.6 to 0.599, and the acetic acid went from 0.7 to 0.701. So it did make a difference. It's just so insignificant compared to the rest of it. It had no effect on the overall pH, which is crazy. So strong acids and strong bases don't have the same effect on buffers as they do on, say, pure water, which makes them kind of useful. We can also use the Henderson-Hasselbalch for problems like this, and this is something I highly recommend you master. It's a really cool skill. If you rewrite the Henderson-Hasselbalch for moles, you end up with this expression where pH equals pKa plus log moles of base minus moles of strong acid divided by moles of weak acid plus moles of strong acid. So in the last problem, the HCl knocked the conjugate base, the acetate, down a little bit. That's why it went from 0.6 to 0.599. But it added to the weak acid. So the acid went from 0.7 to 0.701. And this is the same effect here. You can see how the acid lowers the base, but it ends up adding to the weak acid. So you need pKa minus log of Ka is 4.74. No problems there. You can plug all that stuff in, and when you do that, wow, 4.67. Now, the ice method we used earlier, which I call double ice, because the first ice was taking care of the strong acid, and the second ice table was dealing with the new buffer you had, the new weak acid with its conjugate base. So that's a double ice system. That system gave 4.68. My cool Henderson-Hasselbalch equation here gave 4.67. And unlike the last example where I had to put on more than one slide, I can put all of this on one slide, which is pretty cool. So I do think Henderson-Hasselbalch is a great time saver. It's great about dealing with strong acids and buffers, and as we'll see on the next page, also with strong bases and buffers. It really makes the calculations a lot easier. Double ice is tedious, but man, Henderson-Hasselbalch, rock on. So if you add a strong acid to a buffer, this is the version of the Henderson-Hasselbalch that's used. pH equals pKa plus log. The base goes down with the strong acid, but the weak acid actually goes up with the strong acid. That's how this works. If you add a strong base to the buffer, it's very similar. The strong base will add to the weak conjugate base, but the strong base will lower the weak acid. So you can see kind of the values there are different. Like it's add on the top and subtract on the bottom for the base. The acid was subtract on the top and add on the bottom. And these can be super useful, and I used them sometimes when I made buffers. I highly recommend good old Henderson-Hasselbalch. So here's a question to think about buffers. We're adding a small amount of strong base to a buffer, okay? Now, strong bases will make your pH go up. You'll have an increase in pH. So it's not going to decrease C, D, and E. Those would be acid problems, not base things, okay? So the base is going to make your pH go up, but does it go up from the strong base, or does it go up because of the weak base of the buffer? And I would absolutely argue that it goes up because of the weak base of the buffer. The strong base will be neutralized by the weak acid, and in the process the weak acid concentration will go down, the weak base will increase. So it goes up because of the weak base, and it's a much smaller increase, all right? So that's why these things happen, stuff. It's not the strong base or the strong acid, it's the resulting effect on the conjugate system which makes the changes to the pH, which is kind of a cool thought. There's pictures of Henderson-Hasselbalch. A lot of people talk about Henderson-Hasselbalch, but they don't usually see their pictures. Woohoo, power of the internet. But anyway, let's say that you and I are in the lab. We want to create a buffer with a pH of 4.30. So if you have a pH of 4.30 that you want, that means that hydronium, which is 10 to the minus pH, should be about 5.0 times 10 to the minus 5 moles per liter. Okay, so we look in the stockroom and we find that we have several choices. But of the choices we have, we would like hydronium to be about equal to Ka, or pH about equal to pKa. Because remember, HH is all about pH equals pKa plus log base over acid. And if you start with a pKa, which is close to your pH, that'll be a good start, and then you can fine-tune the ratio from there. But if you only have Ka values, then you want a Ka which is close to hydronium. So in our problem here, we want a pH of 4.30. That's a hydronium of 5.0 times 10 to the minus 5. So what we would like to have is a pKa close to 4.30. And if you only have Ka values, which happens a lot, we would like a Ka close to hydronium, 5.0 times 10 to the minus 5. So the closer you can get your chemicals to those Kas and pKas, the better. That's kind of what it comes down to. So in our stockroom, we find these three buffer combinations. All right, the stockroom never has quite what you want, but these are the things it has. Hydrogen sulfate and sulfate is a weak system, Ka 1.2 times 10 to the minus 2, and if you minus log that to get pKa, 1.92. And you can see there's acetic acid and acetate, and finally the last one is hydrocyanic acid and cyanide. That's a dangerous combination, by the way. We would want to make sure we use gloves and all that kind of stuff. However, it is a viable buffer source, and you can see the Ka and pKa. So hopefully you can realize here that if we want a pH of 4.30, we want a pKa as close to that as possible. And in this list, definitely the acetic acid acetate combination is closest to 4.3. 4.74 versus 4.3, that's closer. The first one, the hydrogen sulfate sulfate, would be probably more acidic, and the last one, HCN CN minus, that would probably be more basic. Now, if you had Ka values, we want 5.0 times 10 to the minus 5 to be as close to our Ka as possible, and that's obviously closest to, again, the acetic acid. The first one would be too big, and the last one, HCN minus, would be too small. So we definitely want to have the acetic acid acetate combination here. That's going to give us a system which is closest to our desired pH level. Equal moles of acetic acid and acetate would create a pH equal to pKa, 4.74. But we want a pH of 4.30. So that means that we want a more acidic buffer system. So it would be nice to know the ratio of acid to base needed to get the buffer to 4.30. So again, that's where pH and pKa would be the same if the acid and base ratio were the same. The base 10 log of 1 equals 0. So pH equals pKa if the acid and base concentration is the same. But we don't want that to be the case. We want a more acidic pH. So it's not too hard to figure this out. And there's different ways to do it. So one way to figure this out is to go back to the Ka expression. Ka equals hydronium times the conjugate base divided by the acid. And if you rearrange this for the acid concentration, hydronium, that's going to, which is 5.0 5.0 times 10 to the minus 5, that's going to equal the acid over base times the Ka, all right? And what we want to do here is we want to find the ratio of the acid to base. We want to find this part. So what we'll do then is we'll take the hydronium, 5.0 times 10 to the minus 5, and divide by the Ka, 1.8 times 10 to the minus 5. And so if you do that, you end up with a ratio 2.8 to 1. And so what this tells you is that for every mole of base, sodium acetate probably, we'd put in, we need 2.8 moles of acetic acid. So we need 2.8 moles of acetic acid for every 1 mole of the base we put in. So if you put 0.1 moles of base in, you'd put 0.28 moles of acid in, and you are good to go. Let's say that we have 0.10 moles of sodium acetate and we have 0.28 moles of acetic acid. You should have a pH of 4.30. And that's kind of the idea here. Once you find the ratio, in this case it's acid over base, you can find then the ratio you need of the base to the acid, acid to the base, stuff like that. Now, to be honest, I probably would have used the Henderson-Hasselbalch equation here because I'm just the HH guy. But anyway, you could also use that pH equals pK plus log base over acid. So pH 4.30, pK 4.74 plus log base over acid. So 4.3 minus 4.74 gives you minus 0.44. You want an anti-base 10 log to get rid of that log part right there. So 10 to the minus 0.44 gives you 0.336. And that equals the base over acid ratio, but we want the acid over base ratio. So I would take the inverse of both sides. I would invert it, and that means go 1 over 0.36, that gives you 2.8, and 1 over base over acid is acid over base. So that's another way to find the acid to base ratio, and either way is fantastic. So at this point, I think it's cool to practice to make sure that you know how this works out. So here's an example of a buffer you can make, 8.4 grams of sodium hydrogen carbonate mixed with 16.0 grams of sodium carbonate. And notice here the hydrogen carbonate has more hydrogen than the carbonate, so the hydrogen carbonate is the acid and the carbonate is the weak base. And from these numbers and the Ka for hydrogen carbonate, you can calculate the pH.
To prepare our buffer solution, we first weigh our conjugate pair, 16.0 grams of sodium carbonate, the weak base, and 8.4 grams of sodium bicarbonate, the weak acid. We dissolve these solids in 100 milliliters of water. The final buffer solution has a volume of about 120 milliliters and a pH of 10.5.
To solve this problem, I would first turn the grams of sodium hydrogen carbonate into moles. That's going to be the moles of the weak acid. I would then turn the grams of sodium carbonate into moles. That's going to be the moles of weak base. Henderson-Hasselbalch, pH equals pKa plus log moles base over moles acid. You can use molarity over molarity, and you can do that, but that would be extra work, so I don't recommend it. You do need the Ka here for the acid. You would need the Ka for hydrogen carbonate, which is on that table. But anyway, if you've done this all, then 10.50 should be your answer. If you don't get that answer, let me know. Reach out to me. I will try to help you to find the right answer. But this is a good way to check yourself. Make sure you're good to go. Buffers are really important in our bodies, all right? As an example of that, we're constantly breathing in oxygen and exhaling CO2. And the CO2 actually has a slight acidic effect. So CO2 in water makes hydrogen carbonate, which is carbonic acid in water, which is really what happens. That makes H plus and HCO3. So HCO3 minus. So exhaling CO2 is actually a way then to get rid of some of the H plus. It gets rid of some of the acid. And as you get rid of acid, it makes it more basic. Exhaling CO2 raises the pH, makes it more basic of our blood. And this is something that medical people can use to their advantage, stuff like that. So there's a lot of examples of this. In addition, our kidneys use buffers and all kinds of things. This is just a main one that people talk about. And I think you'll talk about more in biology too. But buffers are awesome. The last thing we're going to talk about here is titrations. And titrations are a powerful tool for a chemist. And here at Mount Hood, when we do a titration, we can compete with MIT and Caltech and all these places, because with this simple equipment, we can actually do some pretty serious research, which is kind of a cool thing into itself. But anyway, we're going to talk mostly in this section about acid and base titrations. And this is how you can find out what the concentration of your reactant is, or maybe even find what the molar mass is, stuff like that. But in order to do that, you need a titration curve, and the titration curve will come from a pH meter. Indicators work, but honestly, they're kind of cheesy, so I don't recommend them. So pH meters, which is what we'll try to use, are used to determine when the solution has reached the equivalence point. And earlier we talked about what happens when the moles of acid and the moles of base are the same. Equivalence point is an important part of a titration. So in a normal titration, what you have is, like on the picture on the right, you have what's called a burette, which is a long, narrow tube that allows you to accurately control how much of a liquid goes into your solution. And the pH meter will monitor the pH effects that are happening. So in this example, you're adding sodium hydroxide to HCl. So the pH meter starts by reading acidic pHs. You can see it reads 1.30, but as you add more base, that pH will start to jump. And knowing how acids and bases work will make titrations a lot more helpful for you too. This is an example where you're adding sodium hydroxide, probably to acetic acid. And you can see how there's different combinations here that are happening. So the first amount of acetic acid makes the pH go up just a little bit. The second amount of sodium hydroxide, though, makes the pH up go quite a bit until you reach that point right there, which is the equivalence point. And finally, the sodium hydroxide makes the pH go up a lot, and you finally begin to kind of level off once you get to the pH of the sodium hydroxide. So this is kind of an example of a titration. And notice on the far right, it's kind of like an S. So sometimes they call them S curves. And on an S curve, which you definitely see when you have an acid that you start with and you add a base to it, the equivalence point, the steep point in that titration, that's going to be a real important part for chemists. That equivalence point, the midpoint of the steep part there, is where the moles are equal. So as you add a base, the pH will rise, but then finally it's going to level off once you get past equivalence, because then you essentially have only the strong base, sodium hydroxide, to deal with. Eventually it will get very, very close to the concentration of your pure sodium hydroxide.
When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, it splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form two molecules of water. Sodium and chloride ions are left in solution.
If you want to figure out mathematically what the pH should be for a titration, it is possible. And generally what happens is titrations are split up into 4 regions. The initial point, where in this case you only have a strong acid. You have an equivalence point, where the moles of what you're adding, in this case a strong base, equal the moles of what you started with, the strong acid. Then you have the pre-equivalence region. Moles of what you started with are greater than what you ended with. And finally, you have post-equivalence, where the moles of what you're adding are now greater than the moles of what you're starting with. So in a titration, the first thing listed, in this case strong acid, that's what you're starting with. So in this problem, you can see how the pH down here is acidic. It's the pH of a strong acid. But we're slowly adding in the second part. You're adding here a strong base. So overall, this pH is getting more and more basic. So understanding this then allows you to calculate the pH at any range. Now, N stands for moles, and it comes from PV equals nRT, the gas law, even though these aren't gases. N stands for moles. So moles of strong acid, NSA, moles of strong base, NSB. One more thing. At equivalence between a strong acid and and a strong base, you have nothing left that's going to affect pH except water. So the pH at equivalence point should be pretty close to pH of 7, and that's what we're going to see here. We're going to compare that here in a little bit to a weak acid strong base. Those have different pHs at equivalence, but if you have to identify what your acid is, if that pH is about 7, you've got a strong acid. So in this question, it says at equivalence, the pH of a strong acid, strong base titration should be, and it gives you the three choices: less than 7, i.e. acidic; greater than 7, i.e. basic; equal to 7, neutral; or maybe it depends on the concentration of the acid or the base. Okay, so equivalence means the moles are equal. So this means the moles of strong acid equal the moles of strong base. And like we just talked about, and this is pretty important, at equivalence, your pH should be 7, because you have nothing left when the moles are equal that's going to affect pH except water. We talked about how the conjugates of strong acids and strong bases don't affect pH, so you'll have things like NaCl and water, or KNO3 and water, and none of those things affect pH. That's why the pH is going to be 7. If you have a strong acid, strong base titration, you can figure out the pHs of these different points. And we're just going to kind of gloss over them here. But if you're curious, definitely reach out to me. I can tell you more. Initially, you only have a strong acid, so your pH is going to equal the minus log the concentration of the acid, or moles of strong acid divided by volume of strong acid. This is a nice way to do it, because later we'll use the NSA value, the moles of strong acid, in the calculation. Now at the pre-equivalence region, you have more strong acid than you have strong base. So you need to figure out essentially how much extra strong acid you have, and that's what the numerator is saying there. You're going to subtract the moles of strong base from the strong acid to find out how many moles of strong acid are left. And in the denominator, the bottom down there, you want to divide by the total volume of the solution in liters. Now VSA and NSA won't change because you're not changing that, but you will change the amount of strong base. So that's why NSB and VSB will change. But if you calculate them, you can find to amazing accuracy what the pH will be at those points. Now finally, you'll get to the equivalence point. And in this particular problem, it looks like it's about 50 milliliters. And at that point, moles of strong acid equal moles of strong base. You're only going to have water and some neutral salt, which doesn't affect pH. So that's why the pH should be very, very close to 7. So just keep that in the back of your mind. Now, once you get past equivalence, now the strong base dominates. You're going to have more moles of base than acid, so you need to figure out how many extra moles of base you have, and that's what the top part is saying. And remember that 14 plus log hydroxide is one way to calculate the pH of a strong base. Well, that's basically what we're doing here. We're finding the moles of strong base that are left over, dividing by the total volume in liters. That's what the bottom is. You can find the pH at any point in a strong acid plus strong base titration.
Hydroxide ion is a strong base. It can be consumed in the body with a weak acid, such as dihydrogen phosphate ion produced in the kidney. In the reaction, an H+ ion transfers from the acid to the hydroxide ion to form water and HPO4 2- ion, the weak conjugate base of the weak acid.
I used to have a friend that did research, and she would go down to the Caribbean and find different kinds of sea life solutions, like blood or whatever. I don't know what they were. I don't do anything biology. But anyway, she would then scuba dive to get these. Oh, I was jealous. But anyway, she'd come back and then analyze all these new weak acids using these kind of processes. And that was her research. And that's so cool. I still think that's a pretty neat thing. But anyway, I digress. I did things that were dead and stuff. But anyway, that's a personal problem. Nothing you need to worry about. This is an example of a weak acid plus strong base titration, and there are a couple of things that are different here, and it's worth talking about. So begin, the first thing listed is what you start with. So we're going to start with a weak acid here, and then we're going to slowly add a strong base. And like before, we're going to have regions. We're going to have an initial region. We're going to have an equivalence region. There's going to be a pre-equivalence and a post-equivalence region. And again, those are all based on moles. So initially, we'll have only the moles of weak acid, NWA. At equivalence, the moles of weak acid and moles of strong base will be equal. Pre-equivalence, we have more moles of weak acid than strong base, and the post-equivalence means more strong base than weak acid. And we'll have different equations for that. Now, one thing that's really cool though about weak acids is you need to know the Ka. And we're going to see here in a little bit that the half equivalence point allows you to find pKa from pH. The half equivalence point is literally half the volume or half the moles needed to reach equivalence. So in this case, it looks like it took 25 milliliters to get to equivalence. That means 12.5, which is right about there. That's the volume of half equivalence. And if you go up and over to the pH right there, that pH is going to equal pKa. And this is an awesome way to find the Ka for an acid if you don't know what it is. Pretty powerful. If you have a weak acid and strong base, at equivalence, the strong base moles and the weak acid moles have canceled each other out. However, at equivalence, if they're both wiped out, the weak acid has turned into its conjugate base, and base is the operative word. So notice that the equivalence point for a weak acid strong base titration will be basic. It'll be greater than 7. So for this particular problem, it looks like the pH is close to about 9. That's a basic way. So if you don't know if your acid is strong or weak, do a titration. If the equivalence point is greater than 7, you've got a weak acid, which is by far more common than a strong acid, which should give you an equivalence point pH of about 7. The pre-equivalence region will act like a buffer. We can actually use the Henderson-Hasselbalch region equation in there to describe the pH of this buffer system. So you can see like right in here, the pH change is pretty gradual. That's going to be a buffer region. HH equation to the rescue. Big surprise. I love the HH equation. I'll use it anytime I want. It also explains why at half equivalence, pH and pKa are the same. Because if the moles of base are half of the acid, that's going to get you to half equivalence, and pH equals pKa. So just to highlight that last part, if you have a weak acid and strong base titration and you're at equivalence, what will the pH be? And again, at equivalence, the weak acid and strong base moles are equal. They've wiped each other out. However, the weak acid creates its conjugate base, and bases will be basic. That means the pH should be greater than 7. And this is what you see when you have a weak acid and strong base titration, all right? The annihilation of the strong base has destroyed the weak acid, but the weak acid has kind of a surprise left in it. It comes back as a conjugate base, and it's a weak base, but it's basic. pH should be greater than 7. So you can find equations, and we're not going to go through this in great detail. A weak acid pH is minus log square root Ka times Ca, as long as 100 times K is less than C, which it almost always is. So this is a great way to find the initial point pH. Now at pre-equivalence, we're going to use a variant of the mole version when you had a strong base on a buffer, because in the pre-equivalence region, not only do you have the weak acid, but you're starting to make the weak conjugate base as well. So when you do the math, and you don't have to worry about it, pH equals pK plus log the moles of strong base divided by moles of weak acid minus moles of strong base. And so it's pretty cool. You don't have to worry about the volume, but you do need pKa, stuff like that. At equivalence, you have only the conjugate base left over. This is the ugliest equation. However, it's not so bad if you remember that a weak base, pH equals 14 plus log square root Kb times Cb. Now, Kb equals Kw divided by Ka, and probably you were already using Ka, for example, up here in the initial point, so Kw divided by Ka equals Kb, but if you have Kb, you can put that in there. And then the concentration of the base, all the weak acid has now turned into conjugate base, so the moles of weak acid will equal the moles of your conjugate base, and you just need to divide by the total volume. And then finally, at post-equivalence, you have a strong base left over. This looks a lot like the post-equivalence for strong acid, strong base, except instead of subtracting moles of strong acid, you're subtracting moles of weak acid, and of course adding volume of weak acid instead of weak volume of strong acid. But very similar. That's where the strong base dominates, and you're good to go. Differences in titration curves can occur. So strong acids tend to have very sharp equivalence points. So you can see there on the left graph there, that S-curve is very, very sharp. On the other hand, with the weak acids, they're a little bit more gradual. They will depend on the Ka. And as the Kas get smaller and smaller, those S-curves become more like straight curves all the time, which is crazy. Now, also, I wanted to point out how those half equivalent points are really important for weak acids. That's where pH and pKa are the same. So for example, on the graph on the right, which is a weak acid, it looks like 25 milliliters is the equivalence point, 12.5 kind of right there in the middle, that would be the half equivalence. So for this problem, it looks like the pH will be close to 5, and you could do a better job than I could do on my lame iPad here. But anyway, whatever that pH is, that's going to equal your pKa, and then 10 to the minus pKa gives you Ka. So this is an awesome way to find Ka from a graph, which is really cool. But you can also see from the curves there that there are differences and stuff from all that. Good to go. Polyprotic acid will also have a different kind of curve. Now this is for phosphorus acid, and you can see here how there's like two S curves. There's one right here, and there's a second one right there. So the first S curve is when the first H plus pops off. And if you want to find pKa1, if you will, you can go back half the volume to that little X right there. That pH is going to equal your pKa1. However, because we have a second equivalence point, you can see it's right there, you can also find the second half equivalence, and that's going to be halfway between the two equivalence points at that little X right there. And there, that's where pH and pKa2 will be the same. So it's kind of a cool concept, really neat. Sometimes it's difficult to find the third equivalence point. It can be done, but you need some special techniques. We don't need to worry about it, but if polyprotic acids, you can absolutely find Kas and all that same kind of stuff too. Pretty awesome. An indicator can be used when you don't have a pH meter. pH meters are always the way to go. However, indicators can be useful too. An indicator is nothing more than a chemical that changes color under certain pH ranges. So on the right-hand side there, you can see that bromothymol blue. If you have an acidic pH that's less than 6, it'll be kind of a yellow. It's kind of a green in the middle, but greater than 7.5, it actually becomes kind of blue. So it's kind of a cool concept and stuff that can be used. And before the advent of electronics, they used a lot more indicators than they do now. Now this table on the left here shows different indicators that are possible, and there are thousands of indicators. Bromothymol blue is right there. You can see it's yellow kind of to the left there about 6, kind of green in the middle, roughly 6 to 7, and roughly 7.5 or so is where it turns blue. Phenolphthalein, which is right here, is a common indicator used. It turns red when you get a lot of base around. So in acidic solutions, it's colorless, and it turns kind of a red-pink color when it's around a base. So they're kind of helpful, but they're not as cool as pH meters, especially if you want to measure quantities, like find equivalence volumes and pHs, stuff like that. Here's a question where you might want to think about which indicator would be best. And indicators should be kind of calibrated to your equivalence points. So we have here two possibilities. Phenolphthalein, which is on the top right here, and then on the bottom part here we have methyl red, and the question is which one would you want to use. So you can see here that there's like a blue kind of a graph right there, and the blue graph has a steep point, i.e. the equivalence, that's right there, all right? And notice how that's right where the methyl red begins to turn kind of a yellow into more of a red color. So in this example, I would absolutely say that because the equivalence point is at a pH less than 7, you want the color change to occur less than 7 as well. So methyl red would be a much better choice here. Phenolphthalein up until about 8 is a colorless solution, and past 8 it would begin to get kind of a red-pink color. But before 8 it would just look colorless, and that wouldn't be very helpful for our equation right here because we want the equivalence point to reflect itself in the indicator color change. So definitely methyl red would be the better color here. So that's the end of chapter 14, and I really appreciate you spending your time with me here. This is a bigger chapter, but it's all stuff you can do, and there's lots of resources for you to help learn this material better. I do want to point out the types of equilibrium constants handout, so that'll list Ka and Kb, as well as the other equilibrium constants we've seen, and the ones we have yet to see, by the way, too. The Bufferson-Henderson-Hasselbalch guide can be really helpful. It'll talk more about what a buffer is and also how to use the HH equation. And there's other things you can use, the textbook, etc., etc. You can also reach out to the LSC/Avid Center. They'll help you. And of course, I stand ready to help you too, no problem. Thank you for spending your time with me. I hope this has been helpful as you begin to learn this material. And again, reach out to any of us if you have any questions. All right, have a great day.